Okay, welcome. This is the week 7 webinar. So we're officially past the halfway point of the course. So, very important that hopefully things are going well. And let me tell you the plan for this webinar. Well, as always, I'll always answer any questions you might have, and that could be throughout. And then we're going to get into hypothesis testing. It turns out that pretty much just about everything we do for the rest of this entire course, the last, 6 weeks of the whole class, will be about hypothesis testing. Okay, there'll be a few little things here and there, but basically, hypothesis testing is what this class is about for now on. So it's really important you pay attention to today because everything we do after today is going to use today's stuff. So it's very important. So we'll talk about kind of the idea of it. And in fact, you actually learned about hypothesis testing. You didn't learn the word hypothesis testing when you're in middle school. Okay, you may not remember, but it was called the scientific method, and that's something that's taught like to kids. And the hypothesis testing really is the scientific method, but it's a formal way of doing the scientific method. So there's going to be a step-by-step process, and these steps actually they need to go in this order, by the way, and that's going to be very important for what we're doing in this class. And you need to keep with this order. So the first thing is you decide on the null and alternative hypotheses, and you say, okay, what is it you think is true that you want to show, and what's the other side? And that's what the other side is the null hypothesis, and what you think and you want to show is true is the alternative hypothesis. Okay, and you're not going to show it's true, you're going to actually provide evidence to suggest that there's a high probability of it being true. And that's really what statistics is all about. We'll get into type 1 and type 2 errors. It's very important to understand when you come up with a conclusion, you might be wrong. And if you're wrong, what disasters might happen because you're wrong? And we'll talk about the type 1 and type 2 errors as the two ways of being wrong. If you're into health science, for example, you often hear false, you'll hear about false positives and false negatives. Okay, those are the words for type 1 and type 2 error in health science. But in general, we're just going to call them type 1 and type 2 error. Those are statistics words. Then we'll talk about level of significance. It's similar. It's not exactly the same, but it's kind of a similar idea of a confidence level, where when you had a confidence level of, say, 95%, that means you're 95% of the time you're going to be right, if you do it over and over and over again. So level of significance is kind of similar. It turns out, and I have no idea why, but it turns out it's like confidence interval optimistic. You talk about probability being right. Level of significance for hypothesis testing is actually probability being wrong in a way, with some more details, which we'll get into. Then we'll talk about the p-value, and that's kind of how rare the occurrence that you just saw is. Then we'll talk about how do you state the conclusion for a hypothesis test. Then we'll interpret the p-value. We'll interpret the level of significance. And that'll be pretty much all the different things with hypothesis testing. We're going to do examples, and the main examples we're going to look at is going to be the same idea as confidence intervals. That is, one of them is if you have a yes-no survey question, and you want to say, hey, I think the proportion of yeses is higher than this. And then you see. Okay. And the other is when you have a quantitative survey question. And that's when you say, I think the average is bigger than whatever everyone else thinks. Okay. Or maybe smaller or maybe different from. Okay. And those are being the different types that we're going to be looking at. And that's really important to understand. There's the yes-no question, and there is the quantitative survey question. We'll also talk, not completely, but at least partly about Project 2. Okay, next week, actually, we'll have all the information we need. to really go over what you have to do for project two. We're in week 7, and project two is not due till the end of week 11, so you got enough time. So, if you start next week, that's fine too, because that'll be 8, and they'll give you 3 full weeks. Okay. So that is a plan. This is an odd week. Why should you maybe be happy about that? Yeah, no exams. Okay. There's no exams this week. Okay. You do have the regular stuff you have to do. You're going to have a chapter assignment. You're going to have a discussion post that you're going to have to do, but no exam to do. Okay. I only do that on even weeks. I figure that seems reasonable. Okay. So that is the plan. Are there any questions that you might have before I go over hypothesis testing? Okay. If there's no questions, let me see if you might be able to guess this. Okay, this is my opinion, but my guess is you'll agree with me too. In the last 5 years, what do you think the most important statistical analysis in the world was in the last 5 years? Any thoughts? And I figured that's what I'm going to go over at least the beginning. What do you think the most important statistical analysis in the last 5 years was in the world? If you can't come up with it, you'll see my answer and you'll say, "Oh, yeah, I think so too." Or maybe you won't agree with me. Nobody wants to say? Yeah, COVID, and in particular, the COVID vaccination. Okay. So the big question, and again, this was about 4 years ago or so, um, is, they came up and there were a few companies. Pfizer was the first one that actually did it. Okay. Moderna was the other one that did it like within a month. And the big question is, does the vaccination work? Okay. Because it's a brand new thing and you have to worry about it. You have to worry about it. When you have a vaccination that works great, you need to use it. When you have a vaccination that doesn't work at all and has terrible, side effects, you don't want to use it. So I'm going to talk a little bit, next week we'll talk a little more about some of the details of how they were able to decide whether the COVID vaccination worked or not. So let me go over and let's talk about what's called the hypotheses. So at the time, during the amount of time that they were going to use for their testing, because you don't want to do a 10-year test because then COVID is going to become, even worse of a disaster if you have a good vaccination and you can't even use it for 10 years. So they only had a short amount of time to test it on people to see if it actually worked. And working means that the percentage of people who got COVID, who got vaccinated, is less than the percentage of people who got COVID and weren't vaccinated. Does that make sense? Any questions on that? Okay, over the amount of time, I don't remember the number of months that they did it for, but they did it a few months and watched the, cases of the people they tested. Okay, so what you're going to do is you're going to turn that, and you may not like this, but we're going to turn that into math symbols. And this is how you do it. So we have the first piece, this first little bit, and this is really important. We're going to be using this for every week for the rest of the entire course. So get this down. This is an H. H, okay, and by the way, it's not just us. This is a worldwide thing. This isn't me, being like, this is my favorite thing. This is how hypothesis test works. H stands for hypothesis. Okay, and then we have a subscript, and you probably think this is 0. But it turns out that the it's kind of cool little history that the people who came up with this were not Americans. Do you know what the British use for the word zero? I know. Well, if you were in England, it's a British word for it's still English, but it's not American English. It's British English. So I'm going to be it's what everyone uses. So I'm going to say it also. I don't see jumping in. Okay, it's not. Okay, Naught actually. So the way you say this is H naught. Okay, H naught. Okay, and that is what's called the null hypothesis. And then after that, and this is important because I do want you to put in all the symbols, and that is a colon. Okay, if you don't know how to do a under, like a little under thing, you can always do this. You can do the underscore, which is like that little thing above the P next to the zero on a typewriter. Okay, on your keyboard. So that's H naught colon. And then this is very important. What you're going to be looking at for everyone who was in the study was did they get COVID during the time period they watched? And the answer is yes, I got COVID, or no, I did not get COVID. Any questions on that? Okay, and it's really important that you keep that in mind. And that was last week too for confidence intervals, is that if you're dealing with yes, no questions, then we're talking about proportions and we use the letter P. Okay, P for proportion. And at the time, 4% of all people, okay, who didn't get vaccinated at the time over that time period that they were doing the testing got COVID. Okay, and they knew that. They knew how rampant COVID was at the time. Okay, and this right here is called the null hypothesis. It's always going to have an equal sign. That's just a note. It'll always have an equal sign this week. Next week we'll have often several equal signs, but this week we're always going to have an equal sign. Okay. Okay, not next week, actually. In a few weeks we'll have, like 3 weeks, we'll have several. But this week we just have an equal sign, and it'll be either P for proportion. If it was quantitative, so if it was, instead of saying, did you get COVID? If it would say, hey, what was your temperature? They do the head temperature, whatever. What was your temperature a month after? Then that wouldn't be a yes, no question. That would be quantitative. What letter do you use for quantitative? P for proportion. What letter would you use for quantitative? Remember? Very important. And we've used this a lot. All right. I'll give you the word since they're not typing in the mean. Does that help? Remember the letter? The hint is you can't put it in the chat box specifically, but you can spell it out. Let's see, jumping in. Okay, the letter we use if it's quantitative is mu. Do you remember that? That's that Greek letter. Okay, and that's the population mean. Okay, and I do want to emphasize this is for the population. You're not looking at the sample and making a hypothesis about the sample because you know the sample. You're making a hypothesis about the entire population. And that was true with confidence intervals too. And a lot of you made mistakes on your exams and on your typing in your answer to the discussion post. So don't make that mistake when you're doing confidence interval hypothesis testing. We're talking about the population proportion or the population mean. Okay, then the alternative hypothesis. There's actually two ways of doing it. I think the easiest is H sub 1 for the alternative hypothesis. Sometimes you'll see H sub A, but I tend to use H sub 1 because that seems to go after 0 really well. And you'll see both. And then you have a colon. And the alternative hypothesis is what you're trying to show is true. If you are the drug company, right, doing wanting to make money on this vaccination. You want to show that a smaller percentage of people get COVID after getting vaccinated. So the way you write that in symbols is P is less than 0.04. Any questions about stating the null and alternative hypotheses? Any questions? Okay, so that's the first thing you do. The first thing you do is you decide what you want to show and write it out in symbols as the alternative hypothesis is what you want to show. The null hypothesis is if you're wrong. And we always use equal. The next thing you do is you say, what disasters, I'm going to call it, but I usually use the word ramifications, would occur if your sample steered everyone the wrong way. Okay? And there's actually two things that could happen. And I use a COVID example because it's something you can imagine. Okay? One thing that could happen is that you did your sample and you looked at it and you realized that almost nobody got COVID from the people that you were sampling. And by the way, their sample size was 40,000. Okay, so it was actually a very large sample size. Okay, so almost nobody gets COVID after they get the vaccination. Okay, and then you're going to say, well, that means it looks great, it's working. But you still could be wrong, it turns out. Even if almost no one in your sample got COVID, there's still a small chance that it didn't, the sample, they just got lucky and nothing to do with the vaccination. Okay, and that would be a type 1 error. Okay, a type 2 error is kind of the opposite. And that is, let's say a bunch of people did get COVID who got vaccinated. And they just had bad luck. Whereas the vaccination actually really does work, not foolproof, but maybe, only 0.5% of the population instead of 4% of the population would get COVID if they got vaccinated. But the group you looked at just got bad luck. Okay. And then you're going to say, well, this isn't working. We're not going to vaccinate people. That would be a type 2 error. So let's talk about the ramifications. So here are the ramifications for the type 1 error. And by the way, in terms of in shorthand, type 1 means you reject the null hypothesis, and the null hypothesis really was true. Okay? So that means we're going to say, yeah, the population proportion of, if everyone got vaccinated is less than 4%, let's get everyone vaccinated. And then it isn't really less than 4%. Okay? That's the ramifications of a type 1 error. Okay? And in that case, what ends up happening is, yeah, you're able to say it worked because the people who you vaccinated didn't get COVID. And then it doesn't work at all. So the vaccine gets approved because you had statistics and it worked, except the vaccination doesn't work. That would suck. So maybe millions and millions of people would end up getting vaccinated. Okay? I don't know about you, if you got vaccinated or not, but when I got back, I was so tired the next day. Okay? I just slept all day long. Okay? I didn't die or anything, but boy, it was just miserable. The other thing that I did after getting vaccinated, I don't know what you did, but after getting vaccinated, then I visited my family because I figured that I was pretty safe. And I was so if the vaccination doesn't work, then I was overconfident. Okay, maybe I could have given my family or I could have gotten COVID from them. Okay, that would be bad, right? Do you agree? Okay, I want to let you know that when I ask for ramifications, it's the bad stuff that happens because of it. Okay, and there's always bad stuff for these errors. You can always come up with ideas. Any questions on this? Okay. So then there's the type 2 error, and that would mean there's not enough evidence to reject the null hypothesis. We say we fail to reject the null hypothesis. You never accept the null hypothesis, it turns out. You just say, we don't have evidence, because it might have been your sample size was too small. Okay? So you fail to reject the null hypothesis, but the null hypothesis was false. So in that case, what that means is you don't have evidence to show this vaccine works, but it really worked, even though your evidence doesn't show it. Okay? And because of that, the vaccine doesn't get approved. And guess what? Because no one gets vaccinated, because we don't have an approved vaccine, then we're going to have an additional million people or so die of COVID. Okay, that's a terrible ramification, isn't it? Okay. Any questions on the type 1 and type 2 error ramifications? Okay, so let's go to the next step. So again, the first step was to decide what your null and alternative hypotheses are. In other words, what is your study going to trying to show is right? The next step is look at the ramifications of the type 1 and type 2 error. And the next step is decide on the level of significance. Okay. And I'm going to tell you what we're using for our class, and it's very important. I'm glad you are watching this. That you go by what I tell you in this class. It's not always exactly the same throughout the world, but this is most of the time. This is what people do. Okay, so the standard level of significance. Okay, and by the way, level of significance is the probability of a type 1 error. Okay. The standard level of significance is 5%. Okay? Just like the standard confidence level was 95%, confidence level, remember, was like the chance of being right. Okay? Or if you do it many times, then 95% of the time you'll get it right. Similarly, for the level of significance, it has to do with the probability of a type 1 error. That means that if it was bad and you did a study, then you'd have a 5% chance of not showing what you want to show. Okay, so if you're right, okay, then there'd be a 5%. If the null hypothesis is true and you did that study with another study with that many people, then there'd be a 5% chance that you're going to end up falsely concluding that the alternative hypothesis is correct. Okay, we're going to either use 1%, which is 0.01, 5%, that's our standard, which is 0.05, and 10%. Okay, all right. Notice that the level of significance is the probability of a type 1 error. If a type 1 error is really bad, compared to a type 2 error, then you want a smaller chance of it happening. If the type 1 error is not as bad as a type 2 error, as a type 2 error is worse, then you're okay with a higher percent chance of a type 1 error happening. So you're going to go for 10%. If they're kind of equal, being the ramifications of a type 1 and type 2, then we'll go for the standard, which is 0.05. Okay, and that's how we're going to do things in our class. I'll let you know that in social science, they pretty much always use the standard. Medical is a whole different thing. And some other things is a whole different things. So that's just to let you know how things work. The news tends to use 5% on good news stations. Okay. Any questions on this? All right. So now, if you think about the type 1 and type 2 error for our example, what do you think is worse? Do you think it's worse to just feel sick for a day after getting the shot and then it doesn't help, or not getting the shot when you could have and then dying? What do you think is worse? Yeah, I think the second one is much worse. Okay. So if that would be the type 2 error, if the type 2 error is worse, we're going to go for 10%. Okay. So the type 2 error is much worse, I think. And by the way, the letter they tend to use is this. It's the first letter of the Greek alphabet, alpha, is that's how you say it. And that's the letter everyone uses for level of significance. Okay. And by the way, if you don't know how to type an alpha on a like your exam or something, you can type ALPHA. Just like for mu, you can type MU. That's fine if you don't want to use the equation editor. And I'll approve that on your project. On your project, I want you to have the right letters because that you can get help with, and you have plenty of time. Any questions on the level of significance? Okay, so the next step is to collect the data. Okay, and we've already talked a lot about this in the first couple weeks of class. You want a good study, and you want to make sure that you have unbiased data, as much as possible. And you want a sample size large enough that you have good, reliable evidence, all kinds of stuff like that. So you collect the data. The next step is you put the data in your computer and you calculate what's called the p-value. Okay? The p-value turns out to be the probability that if the null hypothesis was correct and you did a study with the same sample size that you just did, then you would get something as extreme as you just got. Okay, I'll give you examples in a bit. Okay, there's a lot of stuff today, by the way, I should let you know, but there's no exam. Okay, then you compare the p-value with the level of significance. So if p is less than alpha, so if you ended up, looking at that vaccination, and you would say there's a really, really rare chance of getting such a small percentage of people getting COVID that you got if the vaccination didn't work, that small percent chance, that would be less than alpha. In our case, it's 0.1. Okay, so we're using 10% as our small percent for this example. Sometimes we'll do 10%, sometimes we'll do 5%, sometimes we'll do 1%. Okay, if p is less than alpha, then we reject the null hypothesis and accept the alternative hypothesis. And you say the alternative hypothesis, I have statistically significant evidence that the alternative hypothesis is true. Doesn't mean you know for sure, but you have statistically significant evidence is the way you word it. If the p-value is bigger than alpha, then you fail to reject the null hypothesis. So if it's not that unlikely to get what you got, if the null hypothesis was true, then you can't say the null hypothesis was false. You don't have evidence. And we say we fail to reject, which is not the same thing as accepting. You never accept the null hypothesis. You only fail to reject. Okay? Any questions on that? Okay. As we learned from a couple weeks ago, if you have a large enough sample size, then the sampling distribution is approximately normal. Okay? And it might look something like this. Okay, and if you look at actually what happened with COVID, it looked just like this. Notice our null hypothesis has a less than, and when it has a less than, that means that we're hoping that we're over to the left, kind of low side, because that's less than. Okay, 0.04, that was the percentage of people who got COVID when they weren't vaccinated. It turned out only 1% of the people who were vaccinated got COVID in the experiment. The p-value is the area. In this case, since we have a less than, that's called a left-tailed test. It's the area under the curve in that area. Okay? And they used a computer, and they found that area was 0.004, which is actually very small. Okay, that is less than 0.1. Any questions on that? Not only is it less than 0.1, but it's actually less than the lowest level of significance that we use, and that's 0.01. So when it is actually less than 0.01, we're going to use the word strong. That means we can like brag, we've got it. So we say there is strong, statistically significant evidence to conclude that the population proportion of vaccinated people who get COVID was less than 0.04. Do you see what the conclusion is? Okay, it's not the same thing as you know for sure. That's why you have to use words like strong statistically significant evidence. Okay, that means that you have a very, very good chance of this conclusion being correct. Any questions on this idea? Okay, and this is real, by the way. Okay, so what did the FDA, Federal Drug Administration, do after this statistics was shown? Hopefully you know. So they did this sample, and what did the government do? This history, but it's what you should expect them to do. Maybe you don't know your history. Should I tell you? They approved the vaccination. And they said, yes, let's recommend getting people getting vaccinated because we have strong statistically significant evidence that this works. Do you see? Doesn't mean you can't get COVID, but it means you have a smaller chance of getting COVID if you get vaccinated. Okay. There's actually more complications than that because if you got COVID, it turns out you got less sick if you were vaccinated than if you didn't. So there was more stuff, but I'm not going to get into all the details. They did testing on that too with p-values. Okay. Any questions on that? Okay. And then it turned out they were right because then millions and millions and millions, I think actually hundreds of millions of people got vaccinated. And it was really clear COVID went down for those who were vaccinated. Okay. So please don't be an anti-vaxxer. Look at statistics. Statistics tells you what is probably correct. So now let's interpret the p-value. Okay. So if the population proportion of all vaccinated people who get COVID is 0.04. Notice this is all vaccinated people, not just the ones that got tested. Okay, not the ones that were in that trial, but everyone who could ever get vaccinated. And if that really is 0.04, and if another study of it's a little complicated. There were 40,000 originally, but there were 25,000 in what's called the control in the treatment group. And another study of 25,000 were vaccinated and COVID tested and at the end of the testing time, then there would be a 0.4% probability that fewer than 1% of them would get COVID. Notice the 0.4%. That is because that was our p-value. If you move the decimal over two places, you get 0.4. And that's how you take decimals and turn them into percents. Okay, 1%. Actually, that should be 10%. 10%. Fewer than. Actually, let's see. Fewer than 4% of them would get. No, 1%. That was right. Because 1%, that was over here. 1% of the treatment group got COVID. So that's where that is. That 1% is the percentage of people who got it. 4%, that's the p-value, or 0.4%. Okay, let's interpret the level of significance now. Notice there's a lot of writing, by the way. Be ready. If the, and I want you to use my templates, by the way. Okay, if you use AI, I'm going to zap you. Use my templates. AI won't just use these kind of templates. Okay, and not every question will be about COVID, but kind of the same idea. If the population proportion of all vaccinated people who get COVID is 0.04, and if another study of 25,000 were vaccinated in COVID testing during the ending of testing time, then there would be just want to note, what I just read for the interpreting level of significance is exactly the same as the start of interpreting the p-value. So the great thing about being an online student is that you got a computer, you can copy and paste your interpretation of the p-value to the interpretation of level of significance for the first part. Okay, that last bit will be different. So then there would be a 10% probability, because that is our level of significance, that we would end up falsely concluding that fewer than 4% of all, not just our survey, but of all vaccinated people get COVID during those months. Have I lost you on any of this? There's a lot of stuff here. We'll have more examples too. Any questions? Okay. All right. Just a couple notes. One is this is all coming from this distribution. So we're looking at the normal distribution. The mean is going to be assumed to be 0.04 because that was our H naught, P equals 0.04. So that's the center or the mean of the normal distribution. The standard deviation will be the standard error. So you want a small standard error, actually. Okay? You want a small standard error because then if you're to the left, you'll get a lower p-value. How do you get a small standard error? What's the only way, if you were doing this COVID test thing, what's the only way to get a small standard error? How do you get a small standard error? There's only one way. When you are the tester. Do you remember? We talked about it a couple weeks ago. I don't see y'all jumping in. Use a large sample size. The larger the sample size you use, the smaller the standard error will be. Because remember, there was a divided by the square root of n in there. So that's how you get a small standard error. You can't change the standard deviation. That's just there in the population. But you can get a larger sample size. But it's more expensive to get a larger sample size. And sometimes it takes a longer time. So there's all kinds of problems with larger sample size, and they're logistical. Okay, but logistics is important in the real world. Any questions on that? Okay. I'm going to do a few examples. Okay. Here's another example. Okay. I'm not going to go into all the detail that we just did because we only have so much time. All right. So I'm not sure if you're all from Tahoe or not. Are you from Tahoe? Okay. So if you're from Tahoe, there's something called Snapshot Day. I don't know if you've heard of that. It's really kind of cool. And you haven't heard of it. So what it is they get a bunch of volunteers, and I do it every year because I love it. Not because I'm a statistician, by the way. And what they do is they have the volunteers go and do measurements in all the creeks and streams that flow into Lake Tahoe. And they measure all kinds of things. One is pH, and there's turbidity. There's all kinds of things that they measure to see whether things are getting worse or better, do we have a disaster of the flow into Lake Tahoe? Should we be worried? Does that make sense? And it's done every year. It's a bunch of volunteers. Um, and again, we're going to we meet at the college. It's usually towards the end of May, if I remember right. And I can tell you more about it later. And I'm not in charge. I'm just a volunteer. And what they do is they take data. So one of the things you might care about is the following. Does the average pH in the streams that flow into Lake Tahoe differ from 7.0? I don't know if you know, but 7.0, if you haven't had chemistry, 7.0 is the pH of water. And if you have a very low pH, then it's very acidic, which is not good, by the way. And if you have a very high pH, it's called very basic, and that's bad too. Okay, I'm not going to get into the biology and the environmental science of it, but you can, trust me on this stuff. It's a chemistry and biology thing. So maybe you've heard of pH before. So what we want to do is want to say, well, does the average pH in the streams in Tahoe differ from 7.0? Because if it differs from 7.0, then we need to make an effort in rectifying the problem so that we can save our lake. Any questions on the idea? And this is real, by the way. Okay. So then you come up with your null and alternative hypotheses. H naught, that's the null hypothesis. Now we're not talking about a yes/no question, because what you're doing, and I do it every year, is I take a pH reader and I put it into the creek and I hold it for a minute because it takes a little bit to read. Then I look at it and I write down what the pH is. And that's it. Okay. And you get a bunch of volunteers throughout all the creeks all over that flow into Tahoe. So there's like 100 volunteers. So, and by the way, it's a group for each creek. It's not one person. And we measure it. Okay. And if the population mean, which we'll never know, we can only do a sample. If the population mean is 7, that's great. Okay. So the null hypothesis, the population mean is 7. But maybe it's not 7, and then it's not great, and we got to do something about it. So our H1 is mu is not equal to 7. Any questions on that? Okay, this is called a two-tailed test, because if it is very low, that means we're going to reject the null hypothesis. If it's very high, we're going to reject the null hypothesis. It's both sides of the tail, not just a less than. This is a not equal to. Okay, any questions on that? Okay, let's look at the type 1 and type 2 error. Okay, a type 1 error means that we have statistically significant evidence to show that the pH differs from 7 when it really is 7. So we rejected the null hypothesis and said, hey, the pH is not 7, but it really was 7. Okay? And the ramifications are the government's going to fund a very expensive project to mitigate pH issues in the creek. And it didn't even need to be done. Okay? It was a total waste of money because the creeks were fine. Just our sample kind of misled us. Does that make sense? That's a type 1 error. Okay, type 2 is we did the testing. There wasn't evidence to support the claim that the pH differs from 7 when it does. Okay, so we looked at the pH and it wasn't that much different from 7. And we said, hey, it looks like the mean really is around 7. And the government's not going to fund that project to say, let's fix the creeks when we're not even able to show there's a problem. Okay, so no funding will be put into mitigation, but there was a problem. We just weren't able to show it was a problem. And the Lake Tahoe plant and animals will go extinct because that's what happens if the pH is either way above 7 or way below 7. Which is worse, by the way? By the way, this is depends on how you feel. Which do you think is worse? So type 1 or type 2? Do you think it's worse to just waste a whole lot of money? Or do you think it's worse to let the Tahoe plant and animals go extinct? Okay. Yeah. If you're living in Tahoe, I hope you think that type 2 error is worse. If you're living somewhere else, you may care about your money more because you got to pay for it. But I think type 2 is worse. Okay. And if the type 2 is worse, then let's go for the 10%, just like the last example. Does that make sense? Okay. If they were the same, we'd go for 5%, but they're not. I think type 2 is worse. But again, that's my feeling because I live in Tahoe and I care about our lake. Okay. So now we did the experiment. Okay. The sample size was kind of small. We had an N was 15. We were only able to go to 15 creeks. Okay. Can only do so many creeks because you only have so many volunteers, right? The X bar was 6.4. Okay. Do you remember what X bar means? Very important. We've talked about it last couple weeks. What's X bar mean? So jumping in, that's a sample mean. The sample mean was 6.4. Okay. The sample standard deviation was 3.5. Okay. N was 15, which is less than 31. And when you have a sample size less than 31, you have to assume the distribution of the pH levels is normal. So now let's find the test statistic and the p-value. Any guess on how I'm going to find the p-value? Yeah, you go to our calculator. Okay, so let's go to the calculator. Which calculator do you think I need to do? What number? And one help is that we do things in order or somewhat in order in this class. There's a whole bunch for this week, by the way. There's actually 3 for this week. I guess last week had 5, but this week has 3. So what calculator? Yeah, it's 14 because we have statistics. We have X bar and we have the S. So we testing for mean with statistics. Sigma's unknown. In our class, it'll always be unknown. Some professors wanted me to include known. You never know the standard deviation of the population. So, but I did this for some other, colleges. Okay, S was given, and that was 3.5. X bar was 6.4. N was 15. That was a sample size. Mu naught, what that means is the mu in H naught. So I wrote it as mu naught, and that's 7.0. Any questions on that? So that's 7. And then it's either less than, greater than, or not equal to for our hypothesis. We have a not equal to for all alternative hypothesis. So I'm going to click on not equal to. And then I hit calculate. So a few things. One is it's a t statistic. We don't know the population standard deviation, so we're using the t distribution, students t distribution. And the test statistic is negative 0. How about 6639? 4 decimals is enough. And our p-value is 0.5175. Okay. And by the way, below I got a picture. So this will always show up and it shows you the picture. Notice the rejection region is the values at which you're going to reject the null hypothesis. And I did one for 0.1, 0.05, and 0.01. And we can kind of see where these are. Okay. And these are the numbers. So it even tells you what the rejection region is. But the p-value is the most important, and that's what we're going to be using for testing. Okay, if the p-value is 0.5175, is that small enough? Is that small enough to reject the null hypothesis? Okay, so we look at that. P is very large. I mean, it's around 52%. Our level of significance was 10%. 52% or 0.52 is much bigger than 0.1. So no, if you're bigger, then you don't have evidence. Okay? So there is statistically insignificant evidence. Very important. These words have to be used, by the way, for you to get credit. Statistically insignificant evidence to support the claim that the population mean of pH of water that flows into Tahoe differs from 7.0. And notice I'm highlighting and screaming it out, statistically insignificant evidence. And the word population, if those words aren't in there, then, if you were doing this, you'd be losing points. Got it? So very important, another reason you got to watch the webinar. If you just let AI do it for you, it probably won't give you the words I tell you have to use. So just let you know, you better pay attention. So don't just use AI to do your work, please, or it will zap you. Make sure you're understanding it. Make sure you're using the formatting I'm telling you. Okay. What does it mean for the p-value to be 0.5175? If the population mean pH in all creeks that flow into Tahoe is 7, and if we measured another 15 creeks, then there would be a 52% chance that the sample mean for the new study would either be less than 6.4 or greater than 7.6. By the way, we got 6.4. How did I get that number 7.6? Any thoughts? Didn't come out of nowhere. Any thoughts on that? Okay, I don't see it, so let me tell you. 6.4 is 2.9 above, 6.4, sorry, is 0.6 below 7, right? Because our null hypothesis is mu is 7. 6.4 is 0.6 below the mu naught, or the 7. So it's a two-tailed test. So in the picture, what we got was, again, 6.4 on the left-hand side. So the right-hand side, instead of being 0.6 below, it'll be 0.6 above 7. And that's 7.6. Any questions on how I came up with that 7.6? A lot of people have trouble with that, so that's why I want to emphasize it. Any questions on that? Okay. To interpret the level of significance, if the population pH in all creeks that flow into Lake Tahoe is 7, and if we measured another 15 creeks, then there would be a 10% chance that we'd end up falsely concluding that the population pH of creeks that flow into Lake Tahoe differs from 7. Okay. Any questions on that? I'm going to do a bunch of examples today. That's the plan. So we've done 2. We're going to get a few more. Okay, so now let's suppose you want to see if women are not drinking the recommended 2.7 liters per day on average. Okay, I don't know if you know, but that's the amount of fluid you're supposed to drink for women at least. Okay, is 2.7 liters a day. Okay, and if you don't drink enough, there's health issues. Okay, and I think this doesn't count alcohol because you're not supposed to drink a lot of alcohol anyway. All of it's alcohol, that's not good. So this is like water and, maybe orange juice and stuff like that. Okay. Suppose we decided on a 0.01 level of significance. And we looked at a lot of women. And we want to find out whether we get to reject the null hypothesis or not. So what's the next step? What do we have to do to find the test statistic and p-value? How are we going to find it? Calculator, exactly. Will this calculator work? This isn't going to work. So let's go back to the calculator menu. And in this case, we have data and not statistics. So that's number 15. So that was great that you guessed 15. And what I did is I already separated these by commas, so I can copy, I can paste. And here our H1 is mu is less than 2.7. So we're going to use less than. Okay, we don't know sigma, leave it blank. Mu naught is 2.7. And I calculate. Okay. Test statistic is negative 1.936 or so. By the way, if you're doing the assignments on the computer, it will make sure that you do at least enough number of decimals that they want. Okay. It's always okay to do more. The p-value, I'll just put a bunch in, is 0.0305795. Okay, by the way, can you ever get a p-value bigger than 1? What do you think? Can that ever happen? Yeah, you can't because p is a probability. You can't have over 100% chance of something happening. That can never be true. Do you agree? So p-value, if you ever see bigger than 1, scroll to your right, and there's probably like an e negative 4, and that means move the decimal over 4 places. Okay, so that's what that's going to happen. It happens sometimes, so be ready, especially if you're using like a smartphone because that tends to be like off the screen, and you have to scroll. Okay, so now if our level of significance is 0.01, the p-value is bigger than that. So there is statistically insignificant evidence to conclude that the population mean
The bag just had Skims bags.
is a population mean, and what are we looking at? Amount of liters that women drink per day is less than 2.7. Does that mean we can say that, hey, if we can't conclude it's less than 2.7, we can conclude that they're really drinking 2.7? Can we conclude that? Okay, the answer is no. You can never conclude H naught. Don't even think about it. All you can say is that we don't have evidence to show that it's less than 2.7. You can't say that means it equals 2.7. It might be our sample size is too small. Who knows? Okay, so you can't make any conclusion. Just say we have statistically insignificant evidence. Okay. What you can do is you can look at a confidence interval, and then you can be 95% confident that it's within this certain amount, and that tells you something different. Okay, so that's where confidence intervals kind of help. Okay, I have some templates here, and that is a template for the conclusion of the hypothesis test is there is statistically, it'll either be significant or insignificant evidence to support the claim that the population, it'll either be mean or proportion, and then it's whatever you're claiming. Okay, p-value interpretation template, if, and then in words, if the null hypothesis is true, whatever that is in words, and another sample of however many sample size you had was taken, then there would be a, whatever the p-value is, probability, that, and then its results of the new study would be at least extreme as a result of this study. But it shouldn't be so, make sure when that's a template, make sure you fill in the right things. Okay, talk about the study itself. Similarly, for the level of significance, if the null hypothesis is true, whatever that is in words, and if another sample of whatever was taken, then there would be a, and here it's the level of significance probability, that the new study would result in falsely concluding that, and then whatever it means for the alternative hypothesis to be true. Any questions on that? All right, you ready for a current event? I always like to bring in current events, and the great thing about this class is I always can. Okay, and the last couple months, the big thing was we have a new president. Okay, what I'm not going to do is tell you whether you're supposed to like the president or not, but what I can do is I can cite statistical, surveys that were done to talk about the president. That I can do. And here's the question. Do fewer than 50% of all adult Americans approve of the job Trump has done so far? Okay, so a survey was done of 1,001 people, and 47%, and that means 470 in this case, approve of the job Trump has done so far. Okay, by the way, is that less than 50%? What do you think? Okay, that's less than 50%. So we can say, can we say that fewer than 50% of all Americans approve of the job Trump has done so far? Because 40%, 47% is less than 50%. So can we say that? Okay, the answer is no. Because of this word right here, all. Okay, we only have a sample of 1,001 people. Okay, you can't just say, hey, we got less than 50%. So then, hey, that means we got it. No, you need to do statistics. We're going to have to go to the calculator. Okay. And actually, let's write this down. So H naught is P equals 0.5. H1 is P is less than 0.5 because fewer than is less than. Can I use this calculator here? Hypothesis test for the population mean with data calculator. Okay, that's not going to work. So let's go back to the calculator menu. and tell me which calculator I should use. Yeah, 16, because the survey question is, do you approve of the job Trump has done so far? And the answer is either yes or no. So that's a proportion. So I'm going to be looking at 16, hypothesis test for a proportion. N was 1,001. Our X was 470. This really should be X, not N. Our P naught is 0.5 because H naught was that P is 0.5 because that's not the majority. The smallest you can be and not be the majority. We're seeing if it's fewer, so that's a less than, and hit calculate it. Okay, now we're talking about proportions. It's a Z. It's not a T anymore. The test statistic is about 1.928, negative 1.928. So there's our test statistic. The p-value was 0.0269. Okay. This, by the way, is news and politics. So what's the level of significance when you have news and politics, by the way? I've already mentioned that in class, so I mean in the webinar. What should we use? Yeah, 5%, 0.05. So this is certainly less than 0.05. So that means there is statistically significant evidence to support the claim that, and I'm going to copy and paste. Fewer than 50% of all adult Americans approve of the job Trump has done so far. Any questions on this example? Okay, I will let you know that this conclusion is the most important. The interpreting the level of significance and interpreting the p-value is not as important. Okay, I could ask you that in a test, but I will. If I ask you that, I will definitely have also asked you to write down what the conclusion is. Notice, there is statistically, and then it's either significant or insignificant evidence. Okay, that's important. Start there. Okay, any questions on this? Okay. Yeah, that's a good question. Should you use decimals or percentages? And honestly, you should use whatever makes the most sense. Okay, so I use this 50% here because a news article would use 50%. Does that make sense? They wouldn't use a probability of 0.5 because that's like confusing to most people who read the news. So I try to use what's most realistic, if that helps. Okay, so here's another example. Do more than 2/3 of all Americans support the US in taking steps? By the way, the last one was a real study. It was Gallup. I forgot to mention that. I should always cite my source. This is a true source. So the next question is, do more than 2/3 of all Americans support the US in taking steps to try to reduce climate change? Okay. And H naught is P equals 0.6667. You could throw a bunch more sixes, however many you felt like, it doesn't matter. And H1 is that P is greater than that. Okay, because that's what 2/3 is. 2/3 is 2 divided by 3 is a bunch of sixes and then it rounds to 7 for the next one. Okay, any questions so far? Okay, this is an article I just read yesterday from CBS News. And they had a sample size of 2,230. And their sample proportion was 0.70, 70%. Any questions on that so far? Okay, so now we can use this again. But now our sample size is 2,230. How do I get X? How do we get X here? A little bit of math, not too hard. Because I'll let you know, I read the news article and it didn't give X, it gave P hat. Okay, it gave the sample proportion and it gave your sample size. So how do I get X? Ideas? X is the number of people who said yes, by the way. That's what, from the survey, that's what X means. LC jumping in. If 70% or 0.70 was the proportion of people who said yes, and we had a sample size of 2,230, then you take 72%, 70% of 2,230 or 0.70 times 2,230. So I'm going to use scientific calculator. And I'm going to go 0.70 times 2,230. And it gave me 1,561. Any questions on that? Our P naught was 0. Bunch of sixes and a 7. And we want to see, is it greater than that? So I'm going to click on greater than. This is called a right tail test, and we'll see that in a minute. If I hit calculate, now notice the right tail will make you reject because bigger than means that you only reject when you're in the high side. Okay, our p-value is very small. And to save time, I think I'm just going to say the conclusion. There is statistically significant, in fact, there is strong statistically significant evidence, because p-value is less than 0.01, to support the claim that more than 2/3 of all adult Americans, this is where it is, support the US in taking steps to try to reduce climate change. Any questions on that? This is real data, by the way. Okay, I'm not making anything up. This is news. And that's what I love about this class is that I can easily find real stuff. And there's so many important examples. Okay, it's all over the place. Any questions at all on this example? Okay, what I think I'm going to do next is give you a secret word, which is there. And that's because the first word in concluding your hypothesis test conclusion is there. There is statistically significant evidence, or there is statistically insignificant evidence. So I thought there would be a good one that you wouldn't just guess, but it makes sense, doesn't it? So there is a secret word. And what I want to do now is talk about project 2. Okay, so let's go and in the syllabus, here's project 2. And just note, there's some things that have not changed, and I want to strongly tell you this. There's a 25% penalty if you end up not working with a partner or two partners, even better, group of three. Okay. All right. So make sure you find partners. Okay. And that's really important. And just to know, if you go to discussions, there is now a project 2 discussion forum. Nothing's been put in it, but hit reply. I'm looking for a partner because I don't have one, or because my partner dropped the class, or or I need one. You don't write I hated my partner, but you know what I'm talking about. So if you need to find a partner because maybe the partners you used didn't work for you, or maybe you didn't find a partner last time and boy, did you get a bad grade because of that. Um, post in the project 2 discussion board that you need partners. And 3 is always best, because then if someone drops a class, then you still have 2 left. The other is that way there's less work to do because you can, bring it through. Okay. So that's just a note. Some more notes. Same thing. It'll due on Sunday at 8. It'll be on week 11 Sunday, actually. At close to midnight. But I strongly, 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 strongly encourage you. I don't know what else I can do. I strongly encourage you to do it a few days early. Okay, maybe by Tuesday or Wednesday before it's due, so you can send me a draft of your project and I can let you know of all the things you need to change so you can get a better grade. Okay, otherwise you won't know, and then you may not get a good grade. Okay, there's nothing I can do other than plead, beg you. I want you to do well, but that's part of doing well. If you wait until Saturday to start your project before it's due Sunday, that's not good. Okay. Any questions on that piece? Okay. Let's go to project 2. And I'm going to talk about some of this stuff, but we'll talk more about it next time. Because it's really all about next week's stuff, but I can talk a little bit about now. So you're not quite ready yet, but at least I can hint. Okay. So first thing, the purpose of project 2 is to use confidence intervals and hypothesis testing. So that we've learned about. Okay. So you've learned about confidence intervals and you've learned about hypothesis testing to support or show lack of support for a research project. Okay. You must first decide what you're interested in researching, and then you design your study and collect your data. Okay. This is actually going to be very different than the other project in terms of data collection. You do need to identify a client, just like you did last time. And again, it doesn't have to be anything you actually can find a client. I mean, it could be President Trump as your client. if Trump might be interested in what your results would be. Okay, even though, good luck trying to get him to communicate with you. Okay, I'd have no chance because I don't know anyone who knows him, actually. Okay, and then you're going to analyze your data and you're going to see if it supports your hypothesis. You're going to look at the confidence interval. Okay, just a note, and this is something you're not ready, so you're going to wait till next week, but this has to be a hypothesis test and confidence interval for the difference between 2 means. It's due Sunday at 11:59 p.m., but I strongly recommend you do it by Sunday at 8 a.m. because I don't know, what if your electricity went out and you're screwed? Do you see? So pretend it's due 8 a.m. on Sunday, and then you'll do a lot better. Does that make sense? So that's just a note. You should never wait till the last minute. Okay. Okay, so basically this is going to be all about the hypothesis test and the confidence interval. Okay. You are going to have to use a sampling technique, but you're allowed to use convenience sampling if you want to. Okay. Nothing like the last project. The last project was all about the sampling technique. This one, you just have to state what it was, and that's basically it. And you're allowed to use convenience sampling. You don't even have to survey people. You can actually go find data that can be collected online You can even walk into a store and see how much a bunch of things cost, that kind of thing. It's very different. The last one was all about the sampling. This is not all about the sampling. This is all about the confidence interval and the hypothesis test. Okay. And a few notes, you're still going to be using the Google Sheets program. And to let you know, it's the same one, so it should still be in your Google Drive. So let me go to mine. It turns out when you go to the Google Drive, you're going to click to Veristats. Okay, because it's going to be about next week's stuff. I'm not ready to talk about the details yet because you haven't learned it yet. We haven't gotten there. But it'll be the two Veristats. And strongly, you lose a lot of points if you don't copy and paste the important parts of this spreadsheet. Got it? Okay, and that should be in your project paper. Copy and paste. Got it? It's not hard to do. Okay, and I'll show you next week on more of the details. Where was there? No, sorry. There. Okay. So you're going to be talking about the confidence interval. You can talk about the hypothesis test. I want to let you know that it's really important in the confidence interval. You're going to be looking at the lower bound and the upper bound. And you should talk about, based on the lower bound, what decisions might the client make? Based on the upper bound, what decisions might the client make? And those are different, by the way. Okay, and that should be part of your project. Okay. And you can do all the stuff for the hypothesis test. I can't get into all the details because next week's stuff matters too. There's going to be you need to have a whole paragraph, just like last time I said you had to have a whole paragraph on the standard deviation, but now it's the standard error that matters for confidence intervals and hypothesis testing. And whole paragraph, or even better, throughout the whole paper, make sure you refer to it and talk about what it tells you. What does it tell you about the confidence interval? What does it tell you about the hypothesis test? Is the standard error small enough? Okay. If you wanted a confidence interval that was 99% instead of 95%, and how big a sample size would you need to use to have the same standard error? Okay, those are the kind of things you're going to have to do for the project. Okay. So again, this is a lot of hypothesis tests and confidence interval. You should go into detail of the confidence interval. You should go into detail of the hypothesis test. And here's something important. These should be separate portions of your project. Okay, do not in the same paragraph talk about the confidence interval and the hypothesis test. Those are completely separate. And by the way, a project typically, and I told you last time, but some of you didn't listen. Okay, maybe you don't watch the webinars. All I can do is beg, in terms of watching the whole thing and listening to what I tell you. Is a typical good project is like somewhere between 8 and 18 pages. If you give me a 2-page project, it is not going to look good because there's so many details. Okay. I don't tell you how many pages it has to be, but I do tell you all the details, and there's a lot. And you want to read through all this, and I'll go over this next week too. Okay. So that's the main stuff. So make sure that you got your partners set this week. Okay, that should happen this week for sure. And maybe you already have them set because you're going to use the same ones you used last time. Okay, but if you didn't use partners, make sure you get partners. Got it? Okay, so that's important this week. Next week, the important thing is to post on the Project 2 discussion board what your hypothesis test is going to be, who your client is, how you're going to collect your data. Okay, so that I can tell you that this is going to work, or I'll tell you, no, this is not going to work. And also what your survey question is going to be is probably a good idea too. Okay. And sometimes it won't be a survey question. Sometimes it'll be what you're going to be looking at data. Okay. So for example, if you wanted to find out, who typically gets more snow, Heavenly Ski Resort or Kirkwood Ski Resort, then, that's not a survey question. You're going to have to go find data of more than 31 and more than 30 data points for each on does that make sense? Of how much snow they got on different times, different things. Is that clear? Okay, so that is the main stuff about the project. Any questions about the project? I'll go into more detail when we've learned about 2 sample tests next week. But any questions about anything I've said? Okay, if there aren't any questions, then I think we will, stop the recording and call this done. But I'll always take questions after if you want to ask them without it being recorded. So I'm going to stop the recording.